Good noon to one and all present over here. Today I want to discuss with you about the third lecture on electronics, in which we discuss about formation of hole, types of semiconductor, mobility, and other properties related to conductivity of electron inside the semiconductor. So, first of all, we want to discuss about the energy gap in the semiconductor. For the silicon, it is 0.72 electron volt, and for germanium 1.1 electron volt. At the room temperature, conductivity of semiconductor is very less, but as and when temperature increases, then it is shown in this diagram. Electrons will become excited from the valence band and jump into the conduction band. When there is no electron in the valence band, then again electron moves from conduction band to valence band, valence band to conduction band, and at the same time, on the basis of anti-theory given by P.A.M. Dirac, it is clear the hole is formed in the valence band, like 0 is equal to plus 1 and plus minus 1. Suppose minus 1 is here, that is in the conduction band, and minus 1 behaves as electron, then remaining part of 0, that is plus 1, observed as a hole in the valence band. Next point is, in the semiconductor, the conductivity of electrons is observed in the conduction band, and hole exists in the valence band, so hole gives current in the valence band. And in this way, we can say current in the conduction band due to flow of electrons, whereas current in the valence band is due to hole. And this is the main feature of semiconductor. And now we understand there is a difference between conductor and semiconductor. That is, resistivity of semiconductor is 10 to the power minus 5 to 10 to the power 6 ohm meter, whereas conductivity is 10 to the power 5 to 10 to the power minus 6 mho per meter. Temperature coefficient of the resistance of the semiconductor is negative, and it is already clear current flow is due to the formation of hole in the valence band and electrons in the conduction band. Next, we want to discuss about temperature-based properties of the semiconductor. That is, semiconductor behaves as insulator at 0 Kelvin, and as temperature increases, it behaves as the conductor. So I want to say, with the increment of temperature, semiconductor behaves like a conductor, and this is the most important features, and this features is based on negative resistance property of the semiconductor, formation of holes of semiconductor, and again I want to discuss the resistivity graph is obtained, that is the resistivity and temperature related property indicates that the temperature coefficient, resistance temperature coefficient, is negative for the semiconductor. Again, we want to discuss like conductor. Initially, semiconductor is not so good, but by the application of some parameters like increment of temperature and by the formation of hole, and again by the doping, semiconductor will become more advanced. That is, it will become good conductor in special circumstances. And here we focus, here we classify semiconductor on the basis of doping property. So it is two types: intrinsic semiconductor and extrinsic semiconductor. Intrinsic means it is pure, there is no doping, there is no extra impurities in it, whereas in the case of extrinsic semiconductor, either doping with trivalent atoms or pentavalent atoms, because valency of germanium and silicon is 4, and if doping material, doping element, doping atoms are n-type, that is pentavalent, impurity is mixed, then N-type semiconductor is prepared. Similarly, in the P-type semiconductor, doping impurity is trivalent, and in the given diagram, intrinsic semiconductor is shown clearly, that is there are no impurities in it. Similarly, at the absolute temperature, covalent bond of the semiconductor or behaves normal. That is, semiconductor is just like insulator, but when temperature increases, then having formation of holes and electrons, and electrons jump from valence band to conduction band, and now the current inside the intrinsic semiconductor is explained as the current due to electron and current due to hole. Whereas this equation indicates the electron density of the intrinsic semiconductor. Similarly, extrinsic semiconductor is mainly indicates something in place of tetravalent, either trivalent or pentavalent atoms are mixed as impurities on the basis of bombarding process mainly. Then if pentavalent is added, then it forms N-type extrinsic semiconductor, otherwise it is called P-type semiconductor. So here it is shown when in N-type semiconductor, here it is clear, antimony is mixed up, and finally extra electron is available and makes it N-type semiconductor. Again, in the case of P-type semiconductor, trivalent impurities, trivalent atoms are mixed up by the bombardment process mainly, and its ratio maybe 10 is to 1000, maybe 100. And again, conductivity is explained as the inverse of resistivity, and it is explained by sigma is equal to NQ mu, where mu is the mobility, n is the number of charged particles, and q is the charge particle. Similarly, mobility is explained on the basis of kinematic equation V is equal to u plus at. If initial velocity u is equal to 0, then we obtain V is equal to mu e, where mu is the mobility and E is the electric field. So we can say if electric field is of unit value, then velocity is called mobility. That is, at the unit value of applied electric field, which is the velocity of electron, is called mobility. In this way, we can say slowly in the journey of advancement of semiconductor, we observe band theory, we observe formation of holes, we observe negative temperature resistance coefficient, we observe doping process, and finally semiconductor will become most useful, and more of the electric appliances, home electric appliances are semiconductor based technology. Thank you.